Welcome to the deep dive. Today, we're tackling a topic that's absolutely fundamental to modern life, yet, often unseen: how we protect ourselves from electric shock and electrical fires.
Mm,
We've got a really detailed guide with us, built on international IEC standards. Think of this as your express route to understanding electrical safety, what truly matters, without getting lost in the weeds.
right.
We're aiming for those aha moments, the ones that make complex stuff suddenly click.
Exactly.
Yeah.
And you've brought a wealth of information here. Our goal is to really pull out the crucial principles of electrical safety for everyone listening.
Okay.
We want to paint a clear picture of how we're shielded from harm, especially, when things don't go quite according to plan in an electrical system.
Okay, so let's start with the main threat: electric shock. It's not just a little tingle, is it? What's the real danger here?
Absolutely not. Electric shock is basically what happens when an electric current interferes with your body's normal functions. And this can have really severe consequences for your muscles, your heart, even your breathing. And, of course, it can cause burns.
Right.
The severity isn't just about feeling a shock. It really depends on the amount of current, the path it takes through your body, and, crucially, how long it lasts.
So is there like a scale for this? A way to really grasp how dangerous it can be?
Yes, there is. There's a sort of danger scale laid out in IEC 604799. It divides the effects of AC current on the body into 4 zones.
4 zones.
Yeah, based on current strength and time. Zone 1 is usually imperceptible. You wouldn't even notice it.
Okay.
Zone 2 is where you start to feel it, definite sensation.
All right.
Zone 3 can cause reversible things, like muscle contractions you can't control. But Zone 4, that's where it gets truly serious.
Zone 4 sounds bad.
It is. That's where you have the increasing possibility of irreversible effects, including heart fibrillation.
Heart fibrillation, that sounds, well, terrifyingly serious.
It really is. And here's a key takeaway, a really important one. If a current as small as 30 milliamperes, that's tiny, really tiny, flows near your heart and isn't interrupted almost instantly,
Yeah.
it can be fatal.
Wow. 30 milliamps.
It highlights just how critical that rapid protection is.
Yeah.
And it's also worth remembering that electrical fires, which we should definitely talk about later,
We will.
can start from things like overloaded circuits, short circuits, and even tiny electrical sparks called arcs.
Okay, so protection is clearly vital. What's the most basic rule we should know, the fundamental idea?
The fundamental principle, according to IEC 61140, is this. Any part of an electrical system that's normally live and could be dangerous,
Right.
it just shall not be accessible.
Right. Keep away from the live bits.
Exactly. And any parts that you can touch, accessible conductive parts, they shall not become hazardous,
Well-
even if something goes wrong.
Okay, that makes sense.
And this applies both in normal everyday use and if a single fault condition occurs.
That makes perfect sense. Keep the zap zones off limits and make sure anything we touch stays safe. How do we actually do that?
Well, there are several core methods. One is automatic disconnection of the power supply when a fault is detected.
Like a circuit breaker tripping?
Precisely, flipping almost instantly.
Yeah.
Another is using what's called Class 2 insulation. Think of it like having a double layer of protection around the live parts.
Okay, double insulation.
Preventing contact through physical barriers or simply by keeping things out of arm's reach is also key in some situations.
Makes sense.
Then there's something called equipotential bonding. That's basically making sure all the metal parts you could potentially touch are at the same electrical level.
So no voltage difference between them?
Exactly, to prevent shocks. And finally, using isolating transformers can create electrically separate, much safer circuits.
So it's not just one silver bullet, it's a combination of these defenses. Now, the guide you shared talks about different types of protection. Can you break that down for us a bit? Certainly. We can broadly think about 2 main scenarios. There's directly touching a live part. We call that direct contact.
Okay, touching the wire itself.
Yes. And then there's touching something, maybe a metal casing, that has become live because of a fault that's indirect contact.
Right, the sneaky danger.
Exactly. So, to deal with these, we have 2 main categories of protection. Basic protection, which stops you from touching live parts in the first place.
Okay.
And fault protection, which kicks in if a fault makes something normally safe become hazardous.
Let's tackle basic protection first then. How do we stop ourselves from touching those live wires under normal conditions? What are the methods?
There are a few key ways. The most straightforward is making sure all live parts are properly insulated.
Right, covered up.
Yes, with materials that meet specific safety standards. And it's important to know something simple like paint or lacquer That's not enough.
Good point. Not just any coating.
Definitely not. Another very common method is using barriers or enclosures. You see these everywhere. In electrical panels, control cabinets, equipment housings. Yeah, the boxes things come in.
Exactly. And to really prevent direct contact, these need to have a protection level of at least IP2X or IPXXB.
Ah, IP ratings. I've seen those. They tell you how well something is protected against, like fingers in water.
That's it, precisely. Think of the 2 in IP2X as meaning you can't easily stick a finger or something finger-sized in there and touch something live.
Okay, good barrier. What about openings in those boxes, like doors or panels?
Right. Any openings like that should generally only be openable with a tool or a key.
Makes sense. Needs deliberate action.
Or they should only be openable after the power inside is completely switched off. Alternatively, sometimes there's an automatic safety shutter, like a screen, that closes when you open it and can only be removed with a tool.
Gotcha. And the metal parts.
Oh, absolutely crucial.
Yeah.
Any metal parts of these enclosures must be connected to the protective earthing conductor of the electrical system. Very important.
That makes sense for, contained equipment.
Hmm.
What about situations where things aren't necessarily in a box, maybe in specific industrial areas?
Good question. In areas that are only accessible to skilled or trained people, electricians, engineers, folks like that protection might be achieved differently.
How so?
You might use obstacles to physically keep people away from live parts, or simply by placing those live parts far enough out of arm's reach.
So distance as protection.
Yes, but again, only in controlled environments for skilled personnel. This is covered in detail in IEC 603-64441. Lastly, for very specific situations like really low power circuits,
Yeah.
using extra low voltage or ELV, or maybe limiting the energy of any potential discharge, can serve as a basic protection measure.
Okay, that covers how we avoid directly touching live stuff. Makes sense. Now, what about fault protection? What happens when, say, a motor casing becomes live because of an internal fault?
Right, that's exactly what fault protection is designed to handle. There are 2 main elements to it.
Two elements, okay.
First, you need to connect all those exposed metal parts, the motor casing in your example, to the earth. And you create a network that bonds them all together electrically.
Earthing and bonding. Got it.
Your guide covers this in Chapter G, Section 6. The second element is automatic disconnection of the power supply to the part where the fault has occurred.
Cutting the power fast.
Exactly. And it has to happen fast enough to keep the touch voltage, that's the voltage you might feel, if you touch the faulty part, we call it UC, within safe limits for the duration of the fault. Figure F6 in the guide illustrates this concept quite well.
Touch voltage UC. So that's the potential shock you might get if you touch that faulty casing.
Precisely. And as figure F7 shows, there's a direct relationship. The higher that potential touch voltage, the quicker the power needs to be cut off to prevent harm.
Makes sense. Is there a limit?
Yes. The generally accepted safe limit for touch voltage that you could theoretically withstand indefinitely is 50 volts AC.
50 volts AC.
Okay, for DC, it's a bit higher, 120 volts.
Yeah.
Figure F7 also gives us the theoretical maximum disconnection times for different types of electrical systems. You mentioned TN and TT systems earlier.
Yeah, we'll get to those.
Right. It shows the times based on the normal voltage to earth, which we call UO. For instance, in a common 230-volt AC system, the disconnection for things like socket outlets should happen in just a fraction of a second, like 0.4 seconds.
Wow, that's really fast. Okay, so TT and TN systems. We'll definitely need to unpack what those mean.
Yes, absolutely.
Yeah.
We will. But the crucial point here for fault protection is that the system has to be set up so that a fault triggers a rapid automatic disconnection of the power.
And that usually involves?
It usually relies on those exposed metal parts being properly connected to earth. That provides the path for the fault current to flow and trigger the protective device.
Okay. Now, the guide also mentions additional protection using something called high-sensitivity RCDs. That sounds like a really important backup, like a safety net.
It is indeed a very important safety net. While the basic and fault protection measures we've discussed are absolutely essential, real-world experience tells us they're not, well, foolproof.
Things can go wrong.
Things can go wrong. Insulation can degrade over time, accidents happen, maybe maintenance hasn't been kept up, people can be careless, wires get damaged.
Right, wear and tear.
Exactly. Or even accidental contact in unexpected situations, like involving water. So high-sensitivity residual current devices, or RCDs, provide a critical extra layer of safety in these situations.
Okay, RCDs, extra layer.
Think of them as a very, very sensitive alarm system for electrical faults that involve current leaking to Earth.
How do these RCDs actually work? What makes them so sensitive compared to, say, a normal circuit breaker?
Well, they're incredibly fast-acting switches. What they do is detect even very small amounts of electrical current leaking away to Earth.
Leaking away, how?
Well, that leakage could be going through a person, unfortunately, or an animal, or maybe just through damaged insulation or a fault in the wiring somewhere.
Okay.
They work by constantly comparing the current flowing into a circuit with the current flowing out on the neutral wire.
Like balancing scales.
It's exactly like balancing scales. In a healthy, properly functioning circuit, those currents should be perfectly identical. If there's a difference, even a tiny one,
Yeah.
it means some current is taking an unintended path. It's leaking away to Earth somewhere.
And the RCD spots that difference.
Instantly. RCDs designed specifically for protecting people are typically set to trip to switch off the power when they detect a residual current, that difference, of just 30 milliamperes.
30 mA, that sounds incredibly small.
It is tiny. And as figures F9 in your guide illustrate, they react extremely quickly, much faster than the time it would take for that small current to cause serious harm to the human body, especially fibrillation.
So a minuscule imbalance triggers this super fast trip. That's impressive.
Hmm.
Where are these high sensitivity RCDs particularly crucial? Where are they required?
According to the IEC standards, like IEC 60364, they are mandatory for circuits supplying general use power outlets, socket outlets rated up to 32 amps that are likely to be used by ordinary persons.
So basically, our regular wall sockets at home or in the office?
Pretty much, yes. They're also required for mobile equipment rated up to 32 amps that's intended for outdoor use.
Okay, outdoor equipment too.
And also for AC final circuits supplying luminaires, lighting fixtures in dwellings, in homes.
Right. So sockets, outdoor gear, and home lighting.
Yes. Now, while they might not be legally mandated everywhere else, their use is very strongly recommended because they offer such excellent protection against both direct and indirect contact.
A double benefit.
Absolutely. Some best practices even suggest limiting the number of sockets protected by a single high-sensitivity RCD, maybe to around 10, just to help pinpoint faults easier and avoid nuisance tripping.
Good tip.
And importantly, as figure F10 shows, these 30 mA RCDs work effectively with all types of earthing systems we're going to discuss: TT, TN, and IT.
Okay, perfect segue. Let's dive into those earthing systems now. First up, the TT system. What's the core idea behind that setup? How does it work?
Right, the TT system. The key thing to understand about TT is that all the exposed metal parts of the electrical installation, the casings of appliances, metal conduits, etc., are connected to their own dedicated earth electrode, right there at the installation.
Okay, the building has its own earth spike or mat.
Exactly. Now, the power supply itself, like the transformer down the street, is also earthed. But, and this is the crucial point for TT, the power supply earthing point is electrically separate from the installation's earth electrode. They aren't directly connected by a wire.
So they rely on the ground itself as the connection.
Precisely. Because of this separation, if a fault occurs, say a live wire touches a metal casing, the path for the fault current back to the source involves going through the ground twice, through the installation's earth electrode, through the general mass of earth, and then back up through the power supply's earth electrode.
That sounds like it would have quite a bit of resistance.
It generally does. The impedance of this earth fault loop is often quite high. This usually results in a fault current that's relatively low, maybe just a few amps, sometimes more, sometimes less, but often too low to reliably trip traditional overcurrent protection like fuses or standard circuit breakers quickly enough.
Okay, so fuses might not blow fast enough, or at all.
Exactly. And that's why in TT systems, residual current devices are absolutely vital for safety. They are the primary means of achieving automatic disconnection in case of an earth fault.
So the RCD is the main safety net in a TT system because the fault current might be too small for fuses or breakers.
You got it. The RCD detects that leakage current directly, regardless of the loop impedance.
What level of sensitivity are we talking about for these RCDs and TT systems? Is it always 30 mA?
Not necessarily for the main fault protection, although 30 mA RCDs are still needed for that additional protection on sockets and things we just discussed. For the main fault protection in TT, the sensitivity of the RCD, which we call I delta N,
Oh.
is directly related to the resistance of your installation's earth electrode, which we call RA.
Right, the resistance of that spike or mat.
Yes, the rule is that I must be no greater than 50 divided by RA in ohms. So 50 volts divided by the earth electrode resistance gives you the maximum permissible RCD trip current in amps.
Okay, 50 RA. Are there exceptions?
Yes, for certain locations considered higher risk, like temporary installations on construction sites or agricultural and horticultural locations, the requirement is even stricter. There, I need to be no more than 25 divided by RA.
So twice as sensitive, essentially.
Effectively, yes. Figure F12 in the guide gives you a nice visual idea of the maximum permitted earth electrode resistance, RA, for different standard RCD sensitivities at common voltage levels. Basically, the lower your earth resistance, the less sensitive the RCD theoretically needs to be. But using a more sensitive RCD like 300 mA or 100 mA is generally better practice and provides a wider safety margin.
Can you give us a simple example of how this works in practice, just to make it concrete?
Sure, let's imagine the power supply's earth electrode has a resistance of, say, 10 ohms,
Mm-hmm.
Rn, and your building's earth electrode, Ra, has a resistance of 20 ohms.
Okay, 10 ohms at the source, 20 at the building.
If a fault occurs, live wire touches an earth casing, the total loop impedance is roughly Rn plus Ra, so 30 ohms. The fault current, ID, would be the voltage to earth, say 230V, divided by that 30 ohms, which is about 7.7 amps.
7.7 amps. Is it that dangerous?
Well, the current itself might not trip a large fuse, but the touch voltage on that casing would be the fault current times your earth resistance, so 7.7 amps times 20 ohms.
My
It's
God.
154 volts.
Ouch. Yeah, that's definitely dangerous.
Absolutely. But now let's apply the RCD rule. Rn must be 50 Ra. So 50 20 ohms equal 2.5 amps or 2,500 milliamperes.
Okay, so the RCD needs to trip below 2.5 amps.
Right. So if you install a standard 300 newtonly RCD, which is much, much more sensitive than the 2.5 A maximum allowed,
Yeah.
that 7.7 amp fault current is way above its trip threshold. It will see that imbalance instantly and trip very quickly, typically within about 30 milliseconds, cutting off the power long before that 154 volts can cause harm.
Ah, okay. That really clarifies how the RCD sensitivity ties directly into the quality of your earth connection. Lower resistance is better, but the RCD provides the guarantee.
Precisely.
Are there any other specific rules or practical things to consider with TT systems, like disconnection times?
Yes, definitely. As shown in figure F13, for most final circuits in a TT system, those circuits supplying socket outlets up to 63 amps, or fixed equipment up to 32 amps, the maximum time allowed for the power to disconnect in case of a fault is quite short.
How short?
It depends on the voltage to earth,
Yeah.
but for typical 230V systems, it's 0.2 seconds. For lower voltages, it can be slightly longer, up to 0.3 seconds. For voltages above 230V, it gets even shorter, down to 0.04 seconds.
Very quick. And other circuits?
For other types of circuits, like distribution circuits feeding subpanels, the maximum allowed time is longer, typically 1 second. It's also important to know that RCDs come in different types, as illustrated in figure 14. There are general-purpose ones, and then there are selective types, often marked with an S.
Selective RCDs, what's special about them?
They have a built-in time delay. This is really useful for achieving selectivity or discrimination in larger installations.
Meaning?
Meaning you can have, say, a slightly less sensitive time-delayed S-type RCD protecting a whole distribution board, and then standard instantaneous RCDs on the final circuits fed from that board. If a fault occurs on a final circuit, only the downstream instantaneous RCD trips.
Ah, so the fault is isolated locally and the rest of the board stays powered.
Exactly. It prevents unnecessary widespread outages. Very useful. Figure F15 shows this concept.
Okay. What about if equipment has its own earth connection?
Good point. Sometimes a particular piece of equipment, or maybe a group of equipment, might have its own separate earth electrode, perhaps for functional reasons, as shown in figure F16. In that case, fault protection is provided by an RCD specifically located at the circuit breaker for that equipment or group.
And its sensitivity.
Its sensitivity must be chosen based on the resistance of that specific earth electrode, using the same RA rules we discussed, by 50 RA or 25 RA.
Makes sense. One last TT scenario. What if, for some reason, metal parts aren't properly earthed? Maybe a broken wire.
That's where the additional protection from high sensitivity RCDs really shines. In a situation where exposed metal parts might not be reliably connected to earth, maybe in very dry, rocky ground, or if a protective earth wire is damaged or disconnected, a standard fault protection RCD might not see enough current.
Right.
A high sensitivity RCD, 30 mA or less, as depicted in figure F17, can still offer protection. It provides both fault protection, if the earth connection is poor but not totally gone, and crucially, that extra layer of defense against direct contact if someone accidentally touches a live part.
Okay, that gives us a really good picture of TT systems and why RCDs are absolutely paramount there. Now let's switch gears to the TN system. What's the fundamental difference in how this is set up compared to TT?
Right, the TN system. The key principle here is quite different. In a TN system, all the exposed metal parts of the electrical installation are directly connected back to the earth point of the power supply via protective conductors.
So there's a dedicated wire connecting the metal casings back to the source earth, not just through the ground.
Exactly, a metallic connection. Now, there are a few variations of TN.
Variation.
Yes, there's TNC, where a single conductor acts as both the protective earth, PE, and the neutral N. We call this a PE conductor.
Okay, combined PE and neutral, PEM.
Then there's TNS, where the protective earth, PE, and the neutral N are completely separate wires all the way from the power source transformer right through the installation.
Separate PE and N. Got it.
And finally, there's TNCS. This is very common. It's a combination where you have a combined PEN conductor from the supply transformer up to a certain point, usually the entry point of the building.
Yeah.
And then from that point onwards, within the installation, the protective earth and neutral functions are split into separate PE and N conductors. Figure F18 in the guide actually shows a TNC system example.
Okay, TNC, TNS, TNCS. But the key is that direct wire connection back to the source, Earth.
That's the fundamental difference from TT. And because you have this direct metallic path, when an earth fault occurs, live touches earth metal.
Yeah.
It essentially creates a low resistance, low impedance path back to the source. It's almost like a short circuit between the phase conductor and the neutral via the PE or PEN.
So unlike TT, you get a high fault current.
Generally, yes.
Hmm.
It's a significantly higher fault current than you typically see in a TT system. And this high current is what allows traditional overcurrent protection devices, your standard circuit breakers, and fuses to operate quickly and provide the automatic disconnection of supply needed for fault protection.
So in TN, you're relying on the big fault current to trip the breaker or blow the fuse, rather than primarily needing an RCD to detect small leakage.
That's the core principle, yes. However, even though the fault current is high, this rapid disconnection still needs to happen fast enough to prevent dangerous touch voltages from persisting for too long on the faulted equipment.
Right. Safety still depends on speed.
Absolutely. While the utility company's network in a TN system will typically have multiple earth connections along the protected conductor route, consumers are often required, or at least recommended, to have their own earth electrode at their main service entrance as well.
Why? If there's already a wire.
It helps to keep the potential of the protective conductor system close to the actual ground potential, especially under fault conditions, further minimizing touch voltage risks. Larger installations might even have additional earth electrodes spread throughout the site for the same reason.
Okay, belt and braces.
Pretty much. The main goal is always to ensure that if a fault occurs, the resulting earth fault current, which we call EAD, is definitely high enough to operate the chosen protective device, fuse or breaker, within the specified safety time.
And how do you figure out that current?
Well, that current, EI, is usually calculated based on the voltage to earth, UO, and the total impedance of the fault loop, ZS. ZS is basically the sum of all the resistances and reactances the fault current encounters on its path through the phase wire of the fault itself, the protective conductor back to the source, and the source impedance.
Okay, UO divided by Z's.
Sometimes, to be a bit conservative and account for potential voltage drops during a heavy fault, engineers might use a slightly lower voltage in the calculation, like 80% of UO, 0.8 UOZs.
The guide provides an example calculation for TN. Can you briefly walk us through the main idea there without getting lost in the numbers?
Sure. Let's imagine a typical 230V system again. If a fault happens, the voltage on the faulty metal part, the touch voltage, US, will be somewhere between 0 volts and the full phase voltage. We need to cut that off fast.
Right.
The fault loop impedance, Zs, includes the resistance of the phase wire out to the fault, the resistance of the protective earth wire back, plus the impedance of the supply transformer itself.
Okay, the whole loop.
Yes. The example shows that even with a relatively small but realistic loop impedance, because the voltage is significant, 230V, you can get a very high fault current. In the example, it's over 3,500 amps.
Whoa, 3,500 amps.
Yeah, a massive current. And this huge current will cause a standard circuit breaker, especially one with an instantaneous magnetic trip mechanism, to operate almost immediately, well within the required safe disconnection time. That 20% voltage drop consideration we mentioned just ensures the calculated fault current is a bit on the safe side, making sure the device will trip.
That high fault current is really the key to the protection strategy in a TN system then. What are the maximum times allowed for the power to disconnect? Are they different from TT?
They are slightly different in some cases. As shown in figure F19, the maximum disconnection times in TN systems also depend on the nominal voltage to earth, UO. For instance, if UO is between 50 and 120 V AC, the disconnection must happen within zero point 0.8 seconds.
Okay.
If UO is between 120 V and 230 V AC, very common, it needs to be within zero point 0.4 seconds.
zero point 0.4 seconds. Faster than the 120 V case.
Yes. And if UO is between 230 V and 400 VAC, it's even faster, 0.2 seconds. For voltages above 400 V, it's 0.1 seconds.
So faster disconnection times required at higher voltages.
Correct. Now, for circuits that are not final circuits, think of distribution circuits feeding other panels, or circuits supplying large fixed industrial equipment, the maximum disconnection time is generally longer, 5 seconds.
5 seconds for distribution circuits in TN, compared to 1 second in TT.
That's right. The assumption is the risk of someone being in prolonged contact during a fault is lower on those types of circuits.
Okay. Can you still use RCDs in TN systems?
Oh, absolutely. And they often are. They're particularly useful in TNS systems where the neutral and protective earth wires are separate throughout. In TNCS systems, if you want to use an RCD, it's crucial that the RCD is installed after the point where the neutral and PE conductors are separated. You cannot install an RCD on a combined PE conductor.
Right, because it needs to compare current in the phase and neutral only.
Exactly. RCDs provide excellent additional protection in TN systems too.
So, circuit breakers and fuses are the primary protection, reacting to that high fault current. How do they guarantee that disconnection happens within those specific time limits, 0.4 seconds, 0.2 seconds, etc.?
Good question. For circuit breakers, as figure F20 illustrates, they often have what's called an instantaneous magnetic trip unit. This part is designed to react extremely quickly, typically in less than 0.1 seconds, when the current suddenly jumps above a certain preset threshold, which we call IM, instantaneous magnetic setting.
Okay.
So the condition for protection is that the calculated fault current, IM, using UOZs or the 0.8 UOZC method, must be greater than this instantaneous trip setting IM. If it IM, the breaker will trip almost instantly, easily meeting the time limits.
Makes sense. High current hits the magnetic trip, bam. What about fuses? They don't have trip units.
Right, fuses work differently. As shown in figure F21, for fuses, you need to look at the specific fuse's time current characteristic curve. These curves show how long it takes for the fuse wire to melt and break the circuit at different current levels.
Okay, the graph for that fuse type.
Yes. To ensure protection, the calculated fault current, I8, must be significantly greater than the current value, which we call IA, that corresponds to the required disconnection time, like 0.4s or 5s, on that fuse's curve. So the condition is IAE'd, or IAUOZs.
So you need enough fault current to make the fuse blow within the required time limit shown on its curve.
Precisely. The guide gives an example showing how to work backward from the required time in the fuse curve to determine the maximum permissible loop impedance, Zs or Cs, that will still guarantee enough fault current IA to blow the fuse in time.
What if the fault loop impedance in a TN system happens to be higher than ideal? Maybe very long cable runs or poor connections. Could the fault current be too low to trip the breaker or fuse quickly enough?
That's a definite possibility and a potential hazard in TN systems if not addressed. In those situations where the loop impedance, Zs, is too high, resulting in a fault current that might not reliably operate the overcurrent device within the required time.
Yeah, what then?
Well, that's where RCDs become a very valuable addition or even a necessity in a TN system.
Ah, RCDs as a backup again?
Exactly. An RCD's tripping current, like 30 MAA, 100 MAA, 300 MAA, is typically much, much lower than the current needed to quickly trip a standard overcurrent device, IA or M. So even if the fault current isn't high enough for the instantaneous operation of the circuit breaker or fuse,
The RCD will still see it.
the RCD will still detect that imbalance caused by the earth fault current and trip quickly, providing the necessary automatic disconnection. They're often used in sub-distribution boards, and as we know, are frequently required for final circuits, like socket outlets anyway, for that additional protection aspect.
Okay, so RCDs can solve the high impedance problem in TN. Now, the guide also mentions some key things to consider when actually installing a TN system. What are some of the practical do's and don'ts outlined there?
Yes, figure F22 highlights several important practical points for TN systems. Firstly, the protective earth, PE conductor should ideally be connected to Earth at multiple points along its run, especially in larger networks, to keep its potential stable.
Okay, multiple Earth.
And it generally shouldn't be run inside ferromagnetic conduits like steel pipes or attached directly to large steel structures by itself, as this can significantly increase its impedance at power frequencies, which is exactly what you don't want.
Right, keep the impedance low. What about TNC with the combined PEN conductor?
Ah, yes, TNC has specific rules. When connecting an appliance, the incoming PEN conductor must always be connected to the appliance's earth terminal first before it's connected to the neutral terminal. Very important sequence.
Earth first, then neutral.
Got it. Also, for smaller wire sizes, generally below 10 millimeter of copper or 16 millimeter aluminum, and for all movable or flexible cables, you typically have to separate the PEN conductor into distinct PE and N conductors. So the insulation effectively becomes TNS from that point onwards.
Ah, so you can't really run small PEN conductors.
Generally not recommended or allowed by standards for final circuits. And of course, the fundamental requirement is that any earth faults must be reliably cleared by the overcurrent protection devices, the fuses or circuit breakers chosen for the circuit.
Okay. The guide mentions the LV neutral earthing and isolation.
Yes, it touches on the wider system aspects. The low voltage neutral of the supply transformer must be properly earthed. There should usually be isolation capability at the origin of the low voltage installation, like in the main switchboard. And critically, a PN conductor must never be switched or interrupted. If you need to switch the neutral, you must use a switch that also switches all the phase conductors simultaneously, and the PE must remain continuous.
Makes sense. Never break the protective path. Now, calculating that earth fault current and the loop impedance ZIS seems pretty critical for designing TN systems correctly. What are the different ways engineers figure that out?
The guide outlines three main methods, ranging in complexity and accuracy.
Okay, 3 ways.
The most accurate is the method of impedances. This involves meticulously summing up all the individual series impedances, resistances, and reactances of every component in the fault loop. The transformer windings, the phase conductors, the protective conductors, connection points, everything.
Seems complicated.
It can be, yes. You need detailed data for all the components, which isn't always easy to get.
What's the next method?
A more practical approach often used is the method of composition. Here, you estimate the fault current at the end of a circuit based on the known or calculated fault current at the beginning of the circuit. You use simplified formulas or tables to account for the added impedance of the wiring in between. It's less precise than the full impedance method, but often good enough.
Okay, a calculation based on the start point. And the third?
The third is the conventional method. This is often used for determining the maximum permissible length of a final circuit. It makes a simplifying assumption, usually that the voltage at the protective device during the fault remains at least 80% of the nominal voltage.
Okay, assumes 80% voltage.
Then, using this assumed voltage and the required operating current, IA or IM, of the protective device, along with the resistance per meter of the chosen conductors, you can calculate the maximum length of the circuit that will still guarantee the device trips in time. This method works best when the outgoing phase conductor and the return protective conductor are close together, like in a standard cable.
So 3 methods: detailed impedances, composition, and conventional max length.
That's right. And it's worth noting that sophisticated design software, like Schneider Electric's Codial mentioned in the guide, typically uses the more accurate method of impedances for its calculations.
The conventional method for maximum circuit length sounds like a really useful practical tool. Can you tell us a bit more about how that works? Does the guide give formulas or tables?
Yes, it does. The maximum length, LMAX, of a circuit in a TN system, using the conventional method, can be estimated using a specific formula. This formula, shown in figure F23, takes into account key factors like the phase voltage, usually 0.8 UO, the resistivity of the conductor material, different for copper and aluminum, the required operating current, IA, of the protective device for the specified time, and the cross-sectional areas, sizes, of both the phase wire, SFA, and the protective earth wire, SPE.
Okay, so wire size and material matter a lot.
Absolutely. There's also a correction factor, often called M, used in the formula. This factor accounts for the fact that the phase and protective conductors might not be the same size or even the same material. Okay. Figure F24 shows how to determine M.
Right. And then tables.
Yes. Based on this conventional method, the guide provides tables specifically, figures F25 through F28, that give you pre-calculated maximum circuit lengths. These tables cover different scenarios, like different conductor sizes, whether the protection is by circuit breaker or fuse, The specific current settings or ratings of those devices, the type of TN earthing arrangement, like PE wire, same size as phase or half size, and even the tripping curve characteristics of the circuit breakers, AG type B, C, or D for IEC 60898 breakers.
Wow, quite comprehensive tables.
They are very useful for quick checks. They often incorporate that correction factor or implicitly or provide guidance on how to apply it. The guide even walks through an example of using these tables, along with the correction factor, for a specific TNC installation scenario.
Okay, that's helpful. But what happens back in those tricky TN situations where, despite calculations, the fault loop impedance might still be too high? Maybe due to unforeseen site conditions or very long runs? What are the actual solutions the guide suggests?
Right. For those scenarios where the calculated fault current might not be enough to trip the standard overcurrent protection quickly enough, the guide offers several practical solutions, illustrated in figures F29 to F31.
Okay, what's solution one?
Suggestion 1, shown in figure F29, is to use a circuit breaker that has a lower setting for its instantaneous magnetic trip. For example, instead of a standard Type C breaker, which trips magnetically between 5 and 10 times its rated current in, you might use a Type B, 3.5 mentioned, or a special type, like the Schneider Electric Type G mentioned, maybe 2 to 4 ins.
A more sensitive magnetic trip. Any downsides?
The main thing to check is whether this lower trip setting might lead to nuisance tripping from normal transient currents, like the high starting current inrush, when a motor or a bank of fluorescent lights switches on. You need to ensure it's still stable in normal operation.
Okay, what's suggestion two?
Suggestion 2 in figure F30 is often the simplest and most common solution. Install an RCD on the circuit.
We talk about this RCD as a backup.
Exactly. And for just fault protection in a high-impedance TN circuit, it doesn't necessarily need to be a super sensitive 30VA1, though those are still generally required for socket outlets for additional protection. You could use an RCD with a higher sensitivity, perhaps 100 mA, 300 mA, or even into the amps range, depending on the circuit. Its tripping current will still be far below the level needed to trip the overcurrent device, ensuring disconnection. The guide mentions various Schneider RCD products suitable for this.
Okay, RCD is a strong option. What else?
Suggestion 3 is more fundamental.
Mm-hmm.
Increase the size, cross-sectional area of the protective earth conductor, PE or PEN, and or the phase conductor for that circuit.
Bigger wires.
Bigger wires means lower resistance, which means lower overall loop impedance, the Z's, which in turn means a higher fault current, ID. This might then be enough to reliably operate the original overcurrent device.
Makes sense, but potentially more expensive.
It can be, yes. Finally, suggestion 4, shown in figure F31, involves adding supplementary equipotential bonding conductors. This means running extra wires to connect together different exposed conductive parts or extraneous conductive parts, like metal pipes, within the area served by the circuit.
How does that help?
This extra bonding helps to reduce the overall resistance of the earth fault loop path locally, and also helps to keep different metal parts at the same potential during a fault, reducing touch voltage risks. However, the effectiveness needs careful consideration, and the specific bonding shown in figure F31 is noted as not being allowed in TNC systems. For TNC, increasing conductor size, suggestion 3, is the way to go if bonding isn't feasible.
Right, different rules for TNC. Okay, we've covered TT and TN pretty thoroughly. Now let's talk about the third main type, the IT system. This one sounds quite different. The I stands for isolated, right? Isolated from Earth. Why would you do that?
Yes, that's right. The IT system, described starting in section 6.1 of the guide, works on a fundamentally different principle. The I indicates that the power supply system has no direct connection to Earth. Or, if it does have a connection, usually at the neutral point, it's through a very high impedance, typically a resistor of 1,500 ohms or more.
Okay, so either floating or earthed through a big resistor. But what about the equipment casings?
The exposed metal parts of the electrical installation itself, the motor casings, panels, etc., are still earthed. They are connected to their own local earth electrode or system, similar to a TT setup.
So the supply is isolated, but the installation is earthed. What's the advantage of this?
The major advantage and the primary reason for choosing an IT system is continuity of service.
Yeah.
Because the supply isn't directly earthed, if a single fault occurs between a live conductor and an earthed casing,
Yeah.
there's no low impedance path for a large fault current to flow back to the source. The fault current is limited by that high earthing impedance, if present, and the system's natural capacitance to earth. It's usually very small.
So if the first fault doesn't cause a trip, the system keeps running.
Exactly. This is crucial in applications where an immediate, unexpected power shutdown could be dangerous or incredibly disruptive. Think operating theaters in hospitals, critical industrial processes, onboard ships, places where losing power suddenly is unacceptable.
Okay, continuity is key. But if there's no trip, isn't there still a danger?
Well, the first fault current ID is deliberately kept very low. The aim is to ensure that even if this small current flows through the installation's earth electrode resistance, IA, the resulting touch voltage, IDX-RA, remains below a safe threshold, generally considered to be 50 volts. So the first fault is typically not hazardous in itself.
So one fault doesn't shut everything down, and
Mhm.
it's usually not dangerous immediately. That's definitely interesting for critical operations. But if there's no immediate disconnection after that first fault, what keeps things safe long term? What needs to be in place?
That's the crucial part of designing and operating an IT system safely. Because the system continues to run after that first fault, there are several essential safety measures required.
Okay, what are they?
Firstly, you absolutely must have a permanent installation monitoring device, or PM. This device continuously checks the insulation level of the entire system relative to Earth.
Okay, constantly watching the insulation.
Yes, and it must give an alarm, visual, audible, or both, as soon as that first fault occurs, indicating that the insulation integrity has been compromised. Figure F35 shows this, PM.
So an immediate warning. Fault detected.
Precisely. Secondly, there often needs to be a way to limit the voltage that the neutral point of the power supply, if it exists, can rise to relative to Earth during faults.
Okay, voltage limiting.
Thirdly, and this is vital, there must be a procedure, and ideally specific equipment, to quickly locate that first fault so it can be repaired promptly. You can't just ignore the alarm,
Right, find it and fix it. Why is that so important?
because the real danger in an IT system comes if a second fault occurs on a different live conductor before the first one is fixed.
Double fault.
Yes. If that happens, then there must be an automatic, high-speed disconnection of the affected circuit or circuits. This second fault scenario is illustrated in figure F39.
So the first fault is like a warning bell, find and fix me. The second fault triggers the mandatory trip.
You got it. That's the philosophy of the IT system.
How small is that first fault current typically in an IT system? You said it was low.
It's usually very small, often in the order of milliamperes. Figure F32 gives a simplified example. If you have a 1500 ohm resistor connecting the neutral to Earth in a standard 230 on 400 VV system, a direct phase-to-Earth fault results in a fault current through the resistor of only about 230 V 1500, which is around 150 milliamperes.
Okay, 150 million.
And if your installation Earth electrode resistance are, say, 10 ohms, the touch voltage would only be 0.15 A10 equals 1.5 volts. Completely
no.
harmless.
Wow. Yeah, negligible.
Figures F33 and F34 show a more realistic scenario where you also consider the natural capacitance of the electrical cables to Earth. Longer cable runs mean higher capacitance. This capacitance provides another path for leakage current during the first fault.
So capacitance adds to the leakage.
It does, yes. But even with significant cable lengths, this capacitive leakage current, combined with any current through the neutral earthing resistor, if used, usually keeps the total first fault current low enough that the touch voltages remain safe, assuming a reasonable earth electrode resistance, RA.
Okay.
This really underscores why that permanent insulation monitoring, PIM, and the alarm are so critical. You need to know immediately when that first fault occurs so you can locate and repair it quickly, thereby maintaining the high level of safety and reliability that the IT system is designed for.
Right. The system integrity depends on acting on that first fault alarm. Now, what happens when that dreaded second fault actually occurs in an IT system? How does the protection work then?
Okay, the second fault. This is where things change significantly. Remember, the first fault is on one phase, or neutral to Earth. The second fault happens on a different phase, or neutral to Earth, somewhere else in the installation.
Right, two different live conductors faulted to Earth.
Exactly. Now, because all the earthed metal parts within the installation are typically bonded together by the protective earth, PE conductors,
Yeah.
this second fault effectively creates a direct short circuit between those two different live conductors, with the PE conductors and the earth path forming part of the loop.
So it becomes a phase-to-phase or phase-to-neutral short circuit.
Essentially, yes.
Huh.
And this short circuit should cause a high enough current to operate standard overcurrent protective devices, fuses, or circuit breakers very quickly.
Okay, so the second fault looks more like a regular short circuit.
In many ways, yes. However, the exact way this is handled and calculated depends on a Q factor, as depicted in figure F36. Are all the exposed metal parts of the installation interconnected by a common protective earth PE conductor network? Or are some parts earthed individually or in separate groups?
Okay, let's consider the first case, which sounds more typical. All exposed parts are connected to a common PE network. How does the protection work there?
In this scenario, shown conceptually in figure F37, because all the earth parts are bonded together with PE wires, the path for the second fault current doesn't necessarily involve high resistance through the earth electrodes themselves. It flows mainly through the phase conductors and the PE conductors.
So, a low impedance path.
Generally, yes, leading to a high fault current, similar to a short circuit in a TN system. Because of this high current, you can usually rely on conventional overcurrent devices, circuit breakers, and fuses to provide the automatic disconnection required for the second fault.
Okay, standard breakers and fuses work. How do you size them?
To choose the right ratings and settings for these protective devices, you need to calculate the potential short circuit current for this second fault scenario. The methods used are similar to those for calculating short circuit currents in TN systems, the impedance method, composition method, or the conventional method we discussed.
Okay, similar calculations. Any catches?
One important consideration is that the fault loop for a second fault in IT often involves two different circuits, one with the first fault, one with the second. Therefore, when setting the overcurrent protection, it's often prudent, or required by standards, to consider the total loop impedance as being roughly double that of a single comparable circuit in a TN system.
Double the impedance. Why?
Because the fault current has to flow out on one phase, through the fault, through the PE system, back through the second fault, and back to the source on the other phase. It essentially involves the impedance of both circuits' conductors in the loop.
Ah, okay. Longer path, higher impedance. Makes sense. What about systems with a neutral?
Good question. If the IT system includes a distributed neutral conductor, a four-wire system, the lowest short-circuit currents usually occur for faults involving the neutral. Therefore, in these four-wire IT installations, the phase-to-neutral voltage, UO, is typically used in the formulas to determine the required tripping currents for the protective devices.
And if there's no neutral, a three-wire system.
If there's no neutral distributed, then the calculation is based on the phase-to-phase voltage, or ER3UO, instead.
Got it. And the disconnection times for this second fault?
The maximum allowed tripping times for the second fault depend, again, on whether the earth electrodes of the installation and the power supply substation, if any, are interconnected or independent. For installations with bonded exposed parts and interconnected earths, the time limits are generally the same as for TN systems. For example, 0.4s, 0.2s, 5s, depending on voltage and circuit type. If the electrodes are independent, the limits might be closer to those for TT systems.
Okay. And what about that second situation you mentioned, where exposed metal parts are earthed separately or in groups, not all bonded together? How does protection work then?
Right, that's case 2 in the guide. If the exposed parts aren't all connected to a common earthing system, maybe you have separate buildings, each with its own earth electrode, or a specific equipment earthed individually, then a second fault could occur in a different earthing group from the first fault. In this situation, the rules and protection methods effectively become similar to those used in a TT system.
Meaning RCDs are needed.
Meaning you'll generally need additional protection beyond just the overcurrent devices. This usually means using a residual current device, RCD, in conjunction with a circuit breaker for each of those separately earthed groups or pieces of equipment.
Why can't you rely on the overcurrent device here?
Because the separate earth electrodes are only connected back to each other through the general mass of Earth. The impedance of this path for a phase-to-phase fault occurring across two separate earthing groups can be quite high, limited by the resistance of the earth electrodes themselves.
Ah, like the high impedance in TT?
Exactly. This might limit the second fault current to a level that's too low to reliably trip the overcurrent protection quickly enough. Therefore, you need the RCDs to detect the leakage associated with the fault.
What sensitivity RCDs?
Often, more sensitive RCDs are needed here compared to the overcurrent devices. However, there's a catch. The RCD's operating current, IDON, must still be chosen so that it's significantly higher than the expected first fault current for the system to avoid nuisance tripping when only the first fault occurs. Figure F38 shows how that first fault current relates to the system's capacitance, which helps in selecting an appropriate RCD sensitivity that's above the first fault level, but low enough to detect the second fault reliably.
Tricky balance. Okay, so how are the actual protective devices, the breakers, fuses, RCDs, typically implemented in IT systems to handle these potential second fault scenarios, whether as common earthing or separate?
Right, let's look at implementation. For circuit breakers, when you have that common protective earth system, case 1, figure F37, the instantaneous and/or short-time delay trip settings, LIME or ISD, need to be carefully chosen. They need to be low enough to guarantee tripping for a second fault, which, remember, might have roughly double the loop impedance of a TN fault, but high enough to avoid nuisance tripping from normal operational surges like motor starting. The guide provides a formula for estimating the loop resistance, R loop, for this second fault scenario, and calculated the resulting fault current.
Okay, careful setting of the breaker trips. What about fuses?
For fuses, it's similar to TN systems again, referencing figure F21. You need to consult the fuse's time current curve. The expected second fault current, calculated considering the doubled loop impedance, must be significantly higher than the current, I, required to ensure the fuse blows within the specified maximum disconnection time. For example, 5 seconds or less.
Ensure the fuse blows fast enough for the calculated IT second fault current.
Got it.
And RCDs.
RCCBs, residual current circuit breakers without overcurrent protection, are often necessary on IT systems, particularly in case 2, separate earthing, where they provide the primary means of second fault detection. Even in case 1, common earthing, they might be used for additional protection, typically installed on a per-circuit basis.
Okay. Now, the guide also talks specifically about calculating the maximum lengths of circuits in IT systems. How is that determined? It sounds like it might be shorter than in TN.
Yes, that's often the case, especially for 4-wire IT systems. The principle for calculating maximum circuit length in IT is fundamentally the same as in TN. You need to ensure that the protective device, breaker, or fuse will operate correctly within the required time in the event of a fault. But here, the critical fault is the second fault.
Right, the double fault scenario.
Since you can't practically test every possible combination of 2 simultaneous faults on different circuits, the standard approach for calculation is usually based on a conservative assumption. Imagine a first fault occurs at the far end of one circuit, and then a second fault occurs simultaneously at the far end of another identical circuit fed from the same board.
Okay, worst case fault at the end of 2 circuits.
Yes. This approach generally ensures that if such a double fault occurs, only the protective devices for those 2 specific faulty circuits will trip, leaving the rest of the system operational, albeit now in a first fault condition relative to other circuits, which still needs attention.
Right. How does this affect the length calculation compared to TN?
For a 3-phase, 3-wire IT system, no neutral, the voltage driving the second fault current between 2 phases is the phase-to-phase voltage, U or A3UO. The maximum length formula uses this voltage. However, for a 3-phase, 4-wire IT system with a neutral distributed, the most common and often lowest second fault current occurs between a phase and the neutral. So the calculation uses the phase-to-neutral voltage, UO, because the loop impedance in IT is effectively doubled. Using UO in the formula results in a maximum allowed circuit length, Lmax, that is typically about half that of a comparable TN circuit designed using UO.
So 4-wire IT circuits might need to be much shorter than equivalent TN circuits.
Potentially, yes, if relying solely on overcurrent protection. The guide provides specific formulas for calculating Lmax in both 3-wire and 4-wire IT cases, using the relevant voltage, conductor properties, protected device current, IA, and that impedance correction factor, M. It also directs users to the same tables used for TN, figures F25, F28, but advises using a specific correction factor for IT systems found in figure F40. There's also an example calculation using these tables for a 3-phase, 3-wire IT installation.
Good to know about that potential length limitation and the maximum tripping times for the second fault.
As we touched on, they generally reiterate the values used for TN systems, depending on whether the installation and substation earth electrodes are interconnected. Use TN times from Fig F19, or separate. Use TT times from Fig F13.
Okay. What are some of the actual practical things, the specific pieces of equipment you absolutely need to have in place when setting up and running an IT system? It sounds like there are some unique components compared to TT or TN.
Yes, definitely. IT systems require some specialized equipment to function safely and effectively. Figure F42 outlines some of the minimum required functions and gives examples of Schneider Electric devices that can fulfill these roles. Key components typically include
Okay, what's first?
an overvoltage protection device. This is sometimes called a voltage limiter or, historically, a CARDU device. It helps protect the system if the voltage to earth rises too high, perhaps due to resonance or external surges.
Right, over voltage protection. What else?
The neutral earthing impedance, if the system isn't fully isolated. This is usually a high-value resistor, as we discussed, to limit the first fault current.
Okay, the limiting resistor.
Then, critically, the overall earth fault monitor, the Permanent Installation Monitoring Device, PIM, complete with its alarm function. Examples given are the Vigilum IM10 or IM400.
The PM alarm. Got it.
You also need the means for automatic second fault clearance, which is usually the standard overcurrent protection, breakers, fuses. If a neutral is distributed, you often need neutral overcurrent protection as well, typically requiring a 4-pole circuit breaker or a specific RCD type, RCD-MS.
Second fault clearance. And finding the first fault.
Exactly. You need a method for first fault location. This could be a portable testing device used by maintenance staff after an alarm, or increasingly permanently installed systems that can automatically pinpoint the faulty circuit while the system is still live. Examples mentioned include Vigilum XGR plus XRM or XE312 systems. Figure F41 shows a typical layout integrating these key components.
That constant installation monitoring sounds like the real heart of the IT system's safety philosophy. How does that actually work at a basic level? How does it monitor the installation?
The basic principle behind most PIMs is quite clever. They continuously inject a small, specific signal, often a low-frequency AC voltage or sometimes a DC voltage between the electrical system, usually connected at the neutral point or an artificial neutral, and the installation's earth electrode.
Okay, injects a signal.
This injected signal causes a very small current to flow. The path for this current is out through the PIM, into the system conductors, then through all the distributed leakage paths, essentially through the insulation resistance of all the cables and connected equipment back to Earth, and finally returning to the PIM via the earth electrode connection.
So the current depends on the overall insulation quality.
Exactly. The magnitude of this tiny circulating current is directly related to the overall insulation resistance of the entire network to Earth. If the insulation is very good, high resistance, the current will be very small. If the insulation starts to degrade somewhere, resistance drops, more current will flow.
And the P measures this current.
Yes, the PM continuously measures this current. If the current rises a preset threshold, corresponding to the insulation resistance dropping below a certain minimum acceptable level, it triggers the alarm.
Clever.
More advanced modern PIMs can do even more. They can track how this leakage current changes over time, providing trend data that can indicate gradual insulation degradation, allowing for proactive, predictive maintenance before a fault actually occurs.
That's really useful for planned maintenance. The guide shows different ways to locate the fault, too.
Yes, figures F43 to F45 illustrate a range of fault location techniques and equipment. It goes from manual methods, using a portable signal generator and a receiver with a clamp to trace the fault signal along different circuits,
Okay, manual tracing.
to fixed automatic fault location systems. These often involve a central PIM unit connected to detectors installed on each outgoing circuit. These detectors usually use toroidal current transformers, CTs, around the cables. When the main PIM alarms for a first fault, the system can automatically identify which outgoing circuit the fault current is flowing on.
Pinpoints the faulty circuit automatically. Nice.
Yes, indicating the insulation level, warning of low resistance, alarming on a fault, and often allowing remote supervision via communication links like Modbus. The most advanced systems, like the Vigilum example with Modbus integration, offer centralized monitoring, logging of insulation levels and events, and precise fault localization, all feeding into a building management or SCADA system.
So, IT systems can be quite sophisticated in their monitoring and diagnostics. Now, when you're actually setting up these permanent insulation monitoring devices, PIMs, are there any key practical considerations? Where do you connect them? How do you set the alarms?
Good practical questions. The PM is typically connected between the system's neutral point, or an artificial neutral created if there is one, and the main insulation earth electrode.
Okay, neutral to earth connection for the PM.
It's absolutely crucial that the power supply to the PM itself is very reliable. You don't want the monitor failing. So it's often powered directly from the IT system it's monitoring, but through its own dedicated overcurrent protection, a small fuse or breaker.
Makes sense. Protect the protector's power. What about alarm settings?
The alarm threshold settings for the PM are very important. Often, installations will use 2 levels.
2 levels.
Yes. A first, higher resistance threshold, lower alarm current, might be set just below the expected insulation level of a new, healthy installation. This acts as an early warning, indicating gradual degradation or moisture ingress, prompting investigation before a serious fault occurs.
A pre-alarm, sort of?
Exactly. Then a second lower resistance threshold, higher alarm current, is set as the main earth fault alarm, indicating a more definite insulation breakdown that requires immediate location and repair. The guide provides some examples of typical threshold values in kiloohms.
Okay. Any other PM quirks?
Well, it's worth noting that environmental factors like high humidity, especially after a prolonged shutdown, can temporarily lower the overall insulation resistance and might trigger the pre-alarm. This doesn't necessarily mean a permanent fault exists. Also, some sophisticated PM devices can differentiate between the resistive component of the leakage current, which indicates a true insulation breakdown or fault, and the capacitive component, which is natural leakage due to cable capacitance. This helps avoid false alarms and gives a clearer picture of the actual insulation integrity.
Very clever tech. Okay, we've covered the three main earthing systems, TT, TN, IT, in quite some detail now. Thanks for that clarity. The guide has a whole section, section 7, dedicated just to residual current devices, RCDs. We know they're important, especially in TT and as additional protection, but what are some other key things we should understand about them from this section?
Yes, Section 7 really focuses on RCDs as devices whose fundamental operating principle is detecting that imbalance, that residual current flowing to Earth. As we've seen, they are absolutely essential for safety in many scenarios across all types of earthing systems.
Right. The guide shows different shapes and sizes.
It does. Figure F31 shows some of the common physical forms they come in. You have the RCCB, residual current circuit breaker, which is just the RCD mechanism itself. It needs separate overcurrent protection like a fuse or MCB alongside it.
Okay, RCCB needs a partner.
Then there's the RCBO, residual current breaker with overcurrent protection. This combines both the residual current detection and overcurrent protection, like a standard MCB, into a single device. Very convenient for saving space.
RCBO is combined. Got it.
You also have the SRCD, which is an RCD built directly into a socket outlet itself.
Socket with built-in RCD.
And the PRCD, which is a portable residual current device often found on extension cords or as a plug-in adapter, great for temporary setups or using equipment outdoors.
Okay, different forms for different uses. What are the different types inside? You mentioned type AC, A, B before.
Exactly. Figure F33 illustrates these crucial differences in RCD types based on the kind of residual current waveform they're designed to detect reliably. This is really important with modern electronics.
Okay, run through them again.
Sure. Type AT RCDs are the most basic. They are designed to detect purely sinusoidal AC residual currents, the kind you typically get from simple resistive loads or faults in older wiring.
Okay, basic AC.
Type A RCDs are more capable. They can detect the sinusoidal AC currents plus pulsating DC residual currents. These pulsating DC components can be generated by common electronic equipment with rectifiers like computers, washing machines, dimmers. So Type A is suitable for most modern household and general commercial applications.
Type A for AC and pulsating DC, that covers a lot.
It does. But then you have Type B RCDs. These are the most advanced for general use. They detect AC, pulsating DC, and smooth DC residual currents.
Smooth DC, where does that come from?
Smooth DC leakage can be produced by things like three-phase rectifiers, frequency converters, variable speed drives, medical equipment, and importantly, electric vehicle, EV charging stations. If you have smooth DC leakage, a Type A or AC RCD might be blinded. It might not trip, even when a dangerous AC or pulsating DC fault occurs. So Type B is essential for these applications.
Wow, okay. Type B for AC, pulsating DC, and smooth DC. Critical for EV chargers and drives.
Very much so. The guide also mentions Type F, which has specific characteristics tailored for circuits supplying frequency inverters, and even a Type EV, specifically optimized for electric vehicle charging scenarios, though Type B is often used there too.
So choosing the right type of RCD is as important as choosing the right sensitivity.
Absolutely critical for ensuring reliable protection with modern loads. Using the wrong type could mean the RCD doesn't trip when it needs to.
Okay. Now, what about those frustrating times we sometimes hear about when RCDs trip for no apparent reason, nuisance tripping? Does the guide address that?
Yes, that's a valid concern, and Figure F36 touches upon it. Nuisance tripping isn't usually for no reason, but it can be caused by factors other than a dangerous fault.
What?
Often, it's due to the cumulative effect of small, normal operational leakage currents from multiple pieces of electronic equipment connected to the same RCD-protected circuit. Things like IT equipment, switched-mode power supplies, filters on drives, they all have some inherent leakage to Earth during normal operation.
Ah, so lots of small leaks add up.
Exactly. If the sum of these normal leakage currents gets close to the RCD's tripping threshold, e.g. close to 30 MAA, then even a small fluctuation or transient might push it over the edge and cause a trip.
How do you deal with that?
Several ways. Firstly, using the correct type of RCD, A or B instead of AC, can sometimes help, as they might be less susceptible to certain types of noise. Secondly, ensure you don't have too many leaky appliances on one RCD circuit. Maybe split the circuits. Thirdly, in some specific industrial cases where safety isn't compromised, a slightly higher sensitivity threshold, for example, 100 mA instead of 30 mA, might be permissible for fault protection, but this needs careful assessment. And fourthly, implementing proper selectivity, which we discussed earlier,
Right, making sure only the local RCD trips.
is key. That prevents a small issue on one circuit from taking out a much larger section of the installation.
Let's just quickly revisit that coordination or selectivity. How do you technically make sure that if there's a fault, only the RCD closest to it trips and not the main one upstream?
That's the principle of selectivity or discrimination between residual current protective devices, detailed in Figure F40. The goal is to ensure only the protective device immediately upstream of the fault operates, isolating the smallest possible part of the network.
How's it achieved?
It's achieved by carefully coordinating the tripping characteristics of the RCDs installed in series. There are two main aspects to coordinate: sensitivity and time delay.
Okay, sensitivity and time.
For sensitivity discrimination, you generally need the upstream RCD to have a tripping current, that is, at least 3 times higher than the downstream RCD. For example, a 100 mA RCD upstream of a 30 mA RCD.
3 times higher sensitivity upstream.
As a rule of thumb. For time discrimination, you use RCDs with intentional time delays. A standard RCD is instantaneous, but you can install time-delayed RCDs upstream. The most common are selective, or Type S RCDs.
Type S, we mentioned those for TT.
Right. They have a built-in minimum non-tripping time, typically around 40 milliseconds or more, even for large fault currents. This gives the downstream instantaneous RCD enough time to detect the fault and trip first before the upstream Type S RCD operates.
The upstream one waits a moment to see if the downstream one handles it.
Exactly. This creates a reliable time-based selectivity, ensuring the fault is cleared locally. You can cascade these, have an instantaneous RCD on the final circuit, fed by a Type S RCD on the sub-distribution board, which might be fed by an even higher-rated, possibly time-delayed RCD at the main incomer.
Okay, that coordination is really important for usability in larger systems. Now, we've covered a huge amount about protecting against electric shock using earthing and RCDs. What about those other protective measures that were mentioned briefly back in Section 8 of the guide? Can we touch on those?
Yes, Section 8 highlights a few alternative or supplementary protective measures that rely on different principles.
Okay, what are they?
First is extra low voltage, or ELV, covered in Section 8.1. The idea here is simple. Use voltages that are inherently so low that they are considered safe and won't cause a dangerous electric shock even if you touch live parts.
How low is extra low?
The limits vary slightly depending on the standard and conditions, but typically means voltages not exceeding 50 VAC or 120 V ripple-free DC under normal and fault conditions. Think of things like some low-voltage lighting systems or control circuits. There are specific types like SLV, separated ELV, and PLV, protective ELV, which has strict rules about source transformers and circuit separation.
Okay, ELV uses safe low voltage. What else?
Next is electrical separation, described in Section 8.2 and shown in Figure F44. This involves supplying only one item of equipment, or sometimes a group, via a special socket arrangement from an isolating transformer.
An isolating transformer.
Yes. This creates a secondary circuit that is electrically independent or separated from the primary supply and from Earth. Because there's no direct connection to Earth on the secondary side, a single fault from a live conductor to an exposed metal part on that side doesn't create a path for significant fault current to flow.
Like creating a mini IT system for one device.
That's a good way to think of it, yes. It prevents dangerous Earth fault currents for that specific piece of equipment, often used for shaver sockets in bathrooms or for tools in workshops.
Okay, electrical separation via transformers. Third
is the use of Class 2 equipment, also known as double insulated equipment. This is covered in Section 8.3 and Figure F45. This equipment is designed and constructed so that basic protection is provided by the normal insulation, and fault protection is provided by supplementary or reinforced insulation.
Double or reinforced insulation.
Right. There are no exposed metal parts connected to the internal workings in a way that they could become live if the basic insulation fails. Because of this double layer of protection, Class 2 equipment does not require connection to the protective earth conductor for safety.
The equipment with the square within a square symbol.
Exactly. That's the symbol for Class 2.
Yeah.
Think of power tools, kitchen appliances, phone chargers. Many are Class 2.
Okay, Class 2 needs no earth, and the last one.
The last measures mentioned are placing live parts out of arm's reach or providing obstacles, covered in Section 8.4 in Figure F46. This is about preventing contact simply by distance or by using physical barriers that aren't necessarily fully enclosing enclosures.
Just keeping people away.
Yes. But as we mentioned when discussing basic protection, this approach is generally only considered acceptable in locations that are specifically accessible only to skilled or instructed persons, like inside locked electrical switch rooms or substations, as defined in standards like IEC 603-64441. It's not for general public areas.
Right, strictly controlled access for those methods. Okay, that wraps up the various ways we protect ourselves, specifically from electric shock. Now let's turn our attention finally to the risks of electrical fires, as detailed in Section 9 of the guide.
Yes, fire risk is another critical aspect of electrical safety. Section 9.1 points out that fires of electrical origin can be triggered by several different electrical faults or conditions.
Like what?
The main culprits are usually overloads, drawing too much current through a wire for too long, causing overheating; short circuits, very high current, causing rapid, intense heating; earth faults, which can also cause significant current flow and heating, especially if not cleared quickly; and those potentially sneaky electrical sparks called arc faults.
Arc faults, we mentioned them earlier.
Yes. Now, protecting against fires specifically caused by earth faults, covered in Section 9.2, largely relies on the same principles and devices we use for shock protection,
Meaning?
meaning detecting and quickly disconnecting any significant earth leakage currents before they can overheat wiring or connection points and start a fire. RCDs play a key role here too. While 30 mm RCDs are primarily for shock protection, slightly less sensitive RCDs, often with a tripping current of 300 milliamperes or sometimes about 900 milliarrays, are specifically recognized as providing significant protection against fire risks arising from earth faults.
So 300 mA RCD is for fire protection from earth faults.
Yes, that's a common threshold cited in standards for fire protection due to earth leakage. And of course, in IT systems, those permanent insulation monitoring devices, BMAMs we talked about, also play a crucial role in fire prevention by giving those early warnings of insulation breakdown, which could eventually develop into a fault capable of causing a fire if left unattended.
Right, PMs help prevent fires in IT too. Now, what about those arc faults? They sound particularly tricky to deal with from a fire perspective.
They are. Section 9.3 focuses specifically on protection against arc faults in cables and connections. An arc fault is essentially an unintended electrical discharge, a spark or arc, across an insulating gap.
Like a tiny lightning strike in the wiring.
Kind of, yes.
Yeah.
Can happen due to damaged insulation, loose connections, pinched cables, things like that. These arcs generate intense localized heat, which can easily ignite nearby flammable materials like wood, insulation, or dust, starting a fire.
And standard breakers might not see them.
Often not. Arc faults might not draw enough current to trip a standard overcurrent circuit breaker quickly, and because the current might stay within the intended circuit path, not leaking to earth, RCDs might not detect them either.
So a hidden fire hazard.
It can be. That's where arc fault detection devices, or AFDDs, come in. These are specialized protective devices designed specifically to recognize the unique electrical signature, the specific noise and current patterns created by dangerous arc faults.
Okay, AFDDs listen for the arc signature.
Essentially, yes. They analyze the current waveform for characteristic typical of arcing. If they detect a dangerous arc, they immediately disconnect the circuit, just like a breaker or RCD, but triggered by the arc signature.
Where are these AFDDs most important?
They are particularly recommended and sometimes mandated by standards like IEC 603-64442 in locations with sleeping accommodations like bedrooms, places with risks of fire due to the nature of processed or stored materials like woodworking shops or barns, locations with combustible construction materials, and irreplaceable goods. They offer protection against both series arcs, breaks in a single conductor, and parallel arcs, arcs between conductors.
So AFDDs are like a dedicated electrical fire watch specifically for arcsing faults in our wiring and connections. That's good to know about. To bring this all together then, what's the key message from the guide about protecting against both electric shock and electrical fire risks?
Well, Section 9.4 really reinforces the idea that achieving comprehensive electrical safety requires a multi-layered, holistic approach. It's not just one device or one technique.
Layers of safety.
Exactly. It involves applying the principles of basic protection to prevent direct contact with live parts under normal conditions. It requires effective fault protection, usually involving earthing and automatic disconnection via overcurrent devices or RCDs, to handle indirect contact when faults occur. It benefits immensely from the crucial additional protection provided by high-sensitivity 30 mA RCDs, especially for socket outlets and mobile equipment. And finally, it necessitates specific measures like appropriately rated RCDs, for example, A300MA and increasingly AFDDs, to mitigate the distinct risks of electrical fires.
And it all needs to work together.
Absolutely. Proper initial design of the electrical installation according to standards, correct installation practices by qualified personnel, and crucially, regular inspection, testing, and maintenance throughout the life of the installation are all absolutely essential to ensure these protective measures remain effective and provide a safe electrical environment.
This has been an incredibly illuminating deep dive into the often invisible world of electrical safety. Really appreciate you breaking down these complex IEC standards. To summarize for everyone listening, what are the most important things you'd like them to take away from our discussion today?
Okay, three key takeaways, I think. Firstly, the core principles of protecting against electric shock, preventing contact with live parts through things like insulation and enclosures, basic protection, and ensuring rapid automatic disconnection of power in the event of a fault, usually involving good earthing, fault protection.
Basics and fault protection. Got it.
Secondly, residual current devices, RCDs, especially the high-sensitivity 30-min ones, offer a vital supplementary layer of safety. They protect against both direct and indirect contact risks that other measures might miss, and they work across all types of earthing systems. Don't underestimate their importance.
RCDs are critical backups.
Okay.
And third,
And finally, we've explored the different philosophies and characteristics of the main earthing systems. TT, these RCDs, TN, uses high fault current, and IT offers continuity but needs monitoring. Understanding how each system provides safety is key. And alongside shock protection, we also need specific measures like medium sensitivity RCDs and AFDDs to address the real risks of electrical fires.
excellent summary. And it's so important to remember, as you said, while this deep dive gives everyone a solid understanding of the fundamentals based on these international guides, there are always more specific details, national wiring regulations, and local codes that apply in different countries and regions.
Absolutely. This is a foundational overview based on IEC principles. Always consult your local standards and qualified professionals for specific applications and compliance requirements.
Definitely. For those of you listening who are curious to learn more, you might want to perhaps look into the specific electrical codes active in your own country or state.
That would be a great next step. Or perhaps dive deeper into detailed technical specifications and testing requirements for different types of RCDs, or explore the fascinating technology behind how arc fault detection devices actually distinguish dangerous arcs from normal electrical noise.
Lots more to explore. So, a final thought for you, our listener, to take away. Electrical safety is absolutely critical, but it's often a hidden aspect of our modern world that we take for granted. Hopefully, understanding these fundamental principles, how we're protected from shock and fire, empowers you to make more informed decisions, ask better questions, and ultimately contribute to a safer environment for yourself and everyone around you.
Well said. Awareness is the first step.
Thanks so much for joining us on this, well, quite shocking deep dive.
My pleasure. Stay safe out there.